Well, hello and welcome again to our journey into number theory, and we're going to begin chapter 3. Chapter 3 is on the arithmetic functions and Dirichlet multiplication. And this is one of my favourite chapters. I'm going to introduce you to some very dear old friends of mine. These are the arithmetic functions, and we're going to have a look at some of their properties. So, firstly, what is an arithmetic function? Well, it's a function that maps the natural numbers into the complex numbers. Now, for the sake of argument, in this section we're going to have the natural numbers are going to begin, in fact, with 1 rather than 0, so I just make that sometimes quite arbitrary, but so the natural numbers start at 1 in this context. And a function that does that maps the natural numbers into the complex numbers, is called an arithmetic function. Now, if an arithmetic function f has the property that f of ab is f of a, f of b, that is, it splits whenever the GCD of a and b is 1. Remember, we're writing this ab meaning the GCD of a and b. So if a and b are relatively prime and f splits on this, so f of ab is f of a, f of b, then f is said to be a multiplicative function. Now, happily, it turns out that most of our lovely arithmetic functions happen to be the ones that we're most interested in, happen to be multiplicative, and that's a very nice property. If the f splits like this, if f of ab is f of ab for any positive integers a and b, then f is said to be completely multiplicative, and that doesn't happen all that often. It's easy to see then that f of 1 is 1. Trivial, if you put a and b both to be 1, you can prove f of 1 is 1 for any multiplicative function, provided f is not 0. And the nice thing about multiplicative functions, what makes them so interesting, is that a multiplicative function is completely determined by its values at prime powers. That is very, very useful fact. If you've got you get the unique factorization of some integer n in terms of its prime powers, then you can simply apply this numerous times, and if you know what f does to a prime power, you know what it does to the number n. So this is a very useful fact. In this section we're going to look at a number of important examples of multiplicative functions. As I said, I'm going to introduce you to some of my dearest old friends, and I'm going to define a special multiplication called Dirichlet multiplication on this set of functions. And this is a very lovely, Dirichlet multiplication is really very, very interesting and lovely way of analysing these things. So the function values at these functions, of these functions, if you actually draw the graphs of some of these functions I'm going to show you, they're all over the place. They're spasmodic, they're up and down, and you can't see much pattern in them, but what you can do is you can smooth them out by averaging, and that turns out to be very, very interesting, because we can then look at developing estimates of their average rate of growth, and that turns out to be really quite surprising. So we're going to have a look firstly at two very, very well known functions, the so-called divisor functions, sigma and tor. Tor is the number of divisors, and you can count that by simply taking this sum over the divisors of n, and whenever you see a divisor of n you copy 1, and so that will count the number of divisors. And sigma of n is the sum of the divisors, so it's sigma d divides n. So for example, tor of 12 is 6, because the factors of 12 are 1, 2, 3, 4, 6 and 12. There's 6 of those, and if you add up all those factors, 1 plus 2 plus 3 plus 4 plus 6 plus 12, you get 28. So we can calculate sigma and tor fairly easily. Sometimes we're going to refer to sigma 0 of n, and that is the sum of so-called Alicop divisors of n. That is, you don't count n itself, so that'll be just sigma of n minus that number n itself. So you count all the factors of n excepting n. We'll also use this notation for sigma to the k of n. This does not mean the kth power of sigma. What it means is it's the sum of the kth powers of the divisors. So it's the sum over the divisors of n of d to the k for some fixed positive integer k. Now we can, we'd like to get some formulae for these fairly quickly, and here this is very easy. If we take any integer n and uniquely factorise it, then it's pretty clear then that we've got a nice formula for tor of n, because any divisor of n will have this shape, and these beta i's, well, they could be 0 because we might not be counting this prime as in amongst the factors, but the maximum each of the beta i's is going to be is the corresponding alpha i's there. So in other words, we have alpha I plus 1 choices for each exponent here, and then if we just take a product of all of those, that will tell me the number of divisors. Now similarly, we can get a nice formula for sigma of n, and sigma of n turns out to be just this product here. We'll have a look at that bit first. So it's 1 plus, so you take, these are the prime, for each I you get a prime factor, and you take the sum 1 plus pi plus up to pi to the alpha I for each of the prime factors of n. Just before I explain where this comes from, this is a geometric series, so you can write it like this. This becomes clear when you simply look at expanding out these brackets. So you take 1 plus p1 squared up to p1 to the alpha 1, and then you take 1 plus p2 and so on up to finally 1 plus pr. And if you take a deep breath and expand all this out, then you're going to get 1 plus, you'll get p1, and in fact by unique factorisation you're going to get every factor of this number n up here. So every factor is going to consist of a product of primes, where you either take some power of p1 from this bracket, possibly 0, some power of p2 from that bracket, and so on. And that of course means you've added up all the factors of n, and that's exactly what this says here. So this follows from the fundamental theorem of arithmetic. So a quick example of how we can calculate this fairly nicely. So if I take this number 1341648, I prime factorise it, 2 to the 4th times 3 squared be 7, be 11 cubed. To get tor of n, I just increase each of these exponents by 1, so I get 5 before, be 2 before, which is 120. So this number has 120 factors. Now you can use this formula. I generally, unless the power is very large, I generally just do this each time. So for the 2, I can write 1 plus 2 plus 4 plus 8 plus 16, and then multiply by, for this one, 1 plus 3 plus 9, 1 plus 7, then 1 plus 11 plus 121 plus 11 cubed, and then quickly calculate that, and I end up with 4719936. So that is the sum of the factors of this number. Now it's easy to show that sigma and tor are multiplicative. They're not completely multiplicative, since, for example, if you work out tor of 4, you get 3, and that's not equal to tor of 2 times tor of 2, which is 4. And similarly, sigma of 4 is 7, and if you try and write 4 as 2 times 2 and split it, you get a different answer. So sigma and tor are multiplicative, which is nice, but not completely multiplicative. Now, one of my absolutely favourite functions amongst this zoo of arithmetic functions is the so-called Merbius function. And it is extremely important in both number theory in general, in analytic number theory in particular, but it turns up in many other places as well. Now I must confess I get rather annoyed by some number theory books, because they just tell you, they just define mu of n apropos nothing and just says, here it is and this is what we can do with it, but they don't give you any hint as to the motivation of it. And I find that annoying in some sense, because you can motivate this in a very, very nice way, in a very important way, from the point of view of analytic number theory, as follows. Recall that for s bigger than 1, we had this lovely Euler product for zeta of s. This was the Euler product, 1 minus 1 over p to the s. Now p means you're summing over all the primes, and then zeta of s is given by that product. Now what I'm going to do is I'm going to turn it upside down. I'm going to turn both sides of this expression upside down, and you'll see something interesting will happen. So turning it upside down, I don't get the minus 1 here, I just get sigma p, 1 minus p to the s. Now let me write this product out, so I get 1 minus 1 over p to the s, 1 minus 1 over 3 to the s, 1 over 1 minus 5 to the s, and so on. And you take a deep breath and expand it all out, and you'll get a 1 from every bracket, so there's that term. You'll get this 1 times lots of 1s, you'll get this term, you'll get that 1 times lots of 1s, you'll get that 1 times lots of 1s, and then you're going to get that 1 times that 1, and the two minuses will give you a plus here. Then you're going to get minus 1 in 7, and the next one you won't get 8 out of this. You can see that. You won't get 9. You won't get 4. But you will get 10 when you multiply this one by this one, and again there are two minuses make a plus. Now a typical term then in this expansion will have a coefficient of 0 if n happens to contain a square factor, because up here you can see you can't possibly get any square factors in here, and so you won't get any terms if of this sort if n contains a square factor. If n contains an even number of primes, then each prime has a minus attached to it here, and got an even number, then you'll get an even number of minus 1s, which is 1, which is what happened here, for example, with the 6 and the 5. And if you've got an odd number of primes, then you'll get an odd number of these negatives, and you'll get minus 1. So I'm going to define this new function mu of n by taking the value 0 if n is not square free. So if n's got a square factor, the answer is 0. It's going to be 1 if, so when you take your n, if it's square free, it must look like just a product of primes. So if n is a product of primes and there's an even number, then it's 1. And if it's an odd number of primes, you get minus 1. And I'm going to define mu of 1 to be 1. And so this function arises very, very, very naturally when you just take the reciprocal of the zeta function. So in particular, here it is, I've written it down here again in a slightly different way. So here's another way of writing it. It's 1 if n is 1. It's 0 if any square divides n. And it's minus 1 to the r if n is a product of r primes. And of course you see that if r is even, you'll get 1, and you'll get minus 1 if it's odd. So thus mu is 0 if n has a square factor, and we got that by simply taking 1 over zeta and expanding it out as a sum. And so we have this very important statement here that 1 over zeta of s can be written as this sum. We're going to call this a bit later a Dirichlet series. We're going to be looking at series of this type. This is called a Dirichlet series. And so, for example, mu of 12, 12 has a square factor of 4, so that's 0. And 30, its prime factorization is 2b3b5. That's got an odd number of primes, and so it's minus 1. So if you've studied the Dirac delta function, the Merbius function is in some sense a discrete version of the Dirac delta function, as we will see in the following theorem. And that's what, this is what our next theorem 3.1 essentially says. It says if you take the sum of these mu of d's over the divisors of n, then it just looks like the floor of 1 on n, which is a fancy way of saying it's 1 if n is 1, and it's 0 if n is bigger than 1. So in particular, when you add up the, if you add up mu over the divisors, then you get 0, except in the case when n is 1. And the proof of this is fairly straightforward actually. So here it is. That's what we're doing here. You take the sum of the divisors, sum over the divisors of n of mu of d, and you get 0 most of the time, and 1 if n is 1. So it's easy to check. If n is 1, then you only get the first term. Mu of 1 is 1, which is how we defined it. If n is bigger than 1, then I can write n as its unique prime factorisation. And now when I take the sum of over the divisors of n, well, the first divisor of n is 1, so I get mu of 1. The next divisor of n is p1, so I get mu of p1 up to pr. That's taking them in a single fashion. And then I could take these in pairs. I could have p1, p2, or p3, p5, and so on. So I get the sum. I get mu of the pairs of prime factors out of this, and then I'll get mu of triples of prime factors, and so on. Well, mu of 1 is 1. For these ones here, these are all single primes, and so their mu value is -1. And there are primes to choose from, and I've got to pick one of them, so this is r choose 1 times -1. Now for the pairs, I've got r choose 2 ways of picking out the 2 primes, and mu of a product of 2 primes is +1, and so on up to r choose r -1 to the r, if I pick all of the primes. And of course you immediately recognise this is by the binomial theorem. This is just the expansion of 1 -1 to the r, and of course that is 0. So that's a nice little result, that the sum of mu's over the divisor of mu of d, where d is a factor of n, adds up to 0 most of the time. The next little function I want to introduce is the Euler's Totient function, as it's called, which you may have come across. Again, this is quite a well-known function. It's defined by, well, firstly phi of 1 is 1, and then if n is bigger than 1, we define phi of n as the size of this set. So this is the set of all x that is relatively prime to n. So we take a number we take the number of numbers relatively prime to n. That's what this phi of n is. We can write this using this rather strange notation with the dash here. The dash denotes the sum is taken over all integers k that are relatively prime to n. So this is a slightly different sum than you're used to. So you take a sum from k equals 1 to n, but you only take the k's that are relatively prime to n and put a 1 there. So as a simple example here, let me just plonk in a simple example at this point here then. So for example, phi of 12. So 12, the numbers that are relatively prime to 12 are 1, 3, 5, and 7, because 2, 4, 6, 8, 9, and 11. So 2 is not relatively prime, 3 is not relatively prime. 4 is not relatively prime, 5 is, 6 is not, 7 is, 8 is not, 9 is not, 10 is not, 11 is, and so this will take the value 4. Okay, so there's the set of numbers that are relatively prime, and we count the number of elements in that set. We saw this function before in the first chapter, of course, so we previously defined this in one of the earlier chapters, I think in chapter 1. Now, and we also saw the result there that phi of the, if we take n and uniquely prime factorise it, then phi of p to this is just this product. And another way of writing that is to take out the p1 to the alpha 1 up to pr to the alpha r, and then we're left with just 1 minus 1 over p. P divides n times n. We saw that before in the earlier chapter. Now this phi also is multiplicative, so that's a useful fact. Well, just to finish off this little section about multiplicative functions, This next result says that if f is multiplicative and I take a sum over the divisors of this f of d, I get a new function, f of n, and that function also is multiplicative. And that is very useful because we're going to be looking at sums of multiplicative functions over their divisors. And it turns out if the sum over the divisors of a multiplicative function gives you a new function which itself is multiplicative. So the proof of this is fairly straightforward. Again, you take m and n to be relatively prime. So here's the proof of this. You take m and n relatively prime. If you've got a factor d that divides the product of these two, then you can write this d as d1, d2. So I should say perhaps write your d as d1, d2, where d1 divides the m and d2 divides n. And the d1 and d2 are themselves relatively prime. Hence, if you work out capital F of mn, that's the sum over the divisors of mn, fd, then you can split this sum into the product of these two sums. You simply take d1 divides m and d2 divides n of f d1 d2. Little f is multiplicative, so you can split that into 2 bits. And then you can split up this sum into this product. This only works because the d1s and d2s are relatively prime, and that is f of m times f of n. So this is a very nice theorem. It's telling us that if you've got a multiplicative function and you take the sum over the divisors of a multiplicative function, then that function is itself multiplicative. And that is a useful fact that we will exploit in further of our videos.